Today I am going to present lecture on the topic normalization. We have also done normalization in the previous lecture. In that we have covered some of the topics under that come under normalization. Let's have a review of the topics that we have covered under normalization in the previous lecture. First of all, we had discussed database design methodologies. As in case of other design methodologies, there are two methodologies that are used. One is bottom up design methodology, which is also called design by an synthesis. Means first we perform a conceptual schema design using a conceptual model such as ER model, that is entity relationship model, and then map that conceptual design into a set of relations. Second is top down design methodology, which is also called design by analysis. Here we start with a number of groupings of attributes into relations that exist together naturally, and then relations are analyzed individually as well as collectively, leading to further decomposition until all desirable properties are met. So the difference between these two methodologies is that in bottom up design methodology we start with the relationships and then perform the relations, but in case of top down design methodology we start with the relations that exist naturally together naturally, and then we decompose those relations in order to meet all the desirable properties. Next, we had discussed about the goodness of relation schemas at the logical or conceptual level. Here it is checked that how users interpret the relation schemas and the meaning of their attributes. Another is implementation or storage level, where we check that how the tuples in a relation are stored and updated. That means how the data is actually stored in this storage secondary storage medium and gets updated. Then we had discussed about the informal design guidelines for designing the relation schemas. For that we have discussed four informal measures of quality for relation schema design. These were semantics of the attributes, reducing the redundant values in tuples, reducing null values in tuples, and disallowing the possibility of spurious tuple generation. Based on these four formal measures of quality, four guidelines were designed. First guideline says that design a relation schema so that it is easy to explain its meaning. Do not combine attributes from multiple entity types and relationship types into a single relation. Only foreign keys should be used to refer to other entities. So here we can see that according to this guideline, a relation schema should correspond to only one entity type or one relationship type. Only then it will be easy to explain its meaning. If we will combine the attributes of more than one entities or relationship types in a single relation, then it will be confusing for the user to understand that relation. Second guideline: now, mixing attributes of multiple entities may result in redundancy of data in the database. The redundant information in tuples causes two main problems. One is wastage of storage space, another is problem of update anomalies. Now, various update anomalies that may occur are insertion anomalies, deletion anomalies, and modification anomalies. So, guideline 2 states that design a schema that does not suffer from the insertion, deletion, and update anomalies. If there are present any of these anomalies, then note them clearly so that the applications can be made to handle those anomalies in the application programs. Third guideline states that relations should be designed such that their tuples will have as few null values as possible. Attributes that are null frequently could be placed in separate relations with the primary key. If nulls are unavoidable, there may be some situations when we cannot avoid nulls. We have to put the null value in the attributes value. In that case, make sure that they apply in exceptional cases only and do not apply to majority of tuples in the relation. Fourth guideline states that the relations should be designed to satisfy the lossless join condition. This condition, lossless join condition, states that no spurious tuples should be generated by doing a natural join of any relations. Now, spurious tuples are the those tuples or those records in the relations that contain invalid or wrong information. So these were the four informal guidelines for designing the relation schemas. Then we had discussed a formal measure for the design of relation schemas, that was functional dependencies. A functional dependency is defined as a constraint between two sets of attributes in a relation from a database. Given a relation R, a set of attributes X in R is said to functionally determine another set of attributes Y also in R if and only if each X value is associated with at most one Y value, and it is denoted as X arrow Y. That means X is functionally determining the value of Y, or you can say Y is functionally dependent on X. So here pictorially we have represented the functional dependency. If X and Y are two subsets of the relation R, then Y is functionally dependent on X. If this denotes the functional dependency. X is called the left hand side of functional dependency. In short, we have written functional dependency as FD, and Y is called right hand side of functional dependency. Here the set of attributes on the left hand side of the functional dependency is called determinant set, which determines the value of the attributes on the right hand side. And the right hand side on the right hand side, the set of attributes is called dependent set. So this whole figure represents how a functional dependency is represented. There are two types of functional dependencies, means in the variations of functional dependencies is trivial and non-trivial. A functional dependency X and Y is trivial if X is a superset of Y, or you can say Y is a subset of X. Otherwise, it is non-trivial. For example, consider the relation imp project that contains information about the employee and the project on which that employee works. Here, employee ID, imp ID, P number, they collectively represent the primary key for the table. Then R's represent the number of hours the employee works on the particular project. E name represents the employee's name, P name represents the project name, P location represents the project location. Here the functional dependencies that hold are imp ID and P number determines the value of P number, imp ID and project number determines the value of employee ID, employee ID and project number determines the value of hours. Now out of these, now in the first two dependencies, you can see that P number on the right hand side is a subset of a set of attributes on the left hand side. Similarly, in the second dependency, employee ID also belongs to or is a subset of the determinant set, that is imp ID and P number. Therefore, these two dependencies are trivial functional dependencies. But in the third dependency, R's does not belong to the set imp ID and P number, that is R's does not belong to the determinant set. Therefore, this dependency is non-trivial functional dependency. So these were the functional dependencies. There may be functional dependencies which are given along with the relation, but there are some rules from which we can reduce or deduce or infer some more functional dependencies for the relation. Armstrong's given some inference rules. First rule was reflexive rule, which states that if Y is subset of X, then X functionally determines Y. That is, according to reflexive rule, trivial functional dependencies always holds always. That means reflexive rule infer the trivial dependencies. Augmentation rule says that if X functionally determines Y, then by adding Z, a set of attributes to both sides, that is to the left hand side and to the right hand side of functional dependency, then that functional dependency also holds. That is, X union Z determines the Y union Z. Third is transitive rule, which says that if x functionally determines y and y in turn functionally determines z, then it infers that x functionally determines z through y. So these rules, a reflexive, augmentation, and transitive, they form a sound and complete set of inference rules. There are some additional useful inference rules in addition to these three Armstrong's rules. One is decomposition or projective rule. If x functionally determines the union of y and z, then x functionally determines y alone as well as x functionally determines z alone. Second is union or additive rule. It says that if x functionally determines y and if x also functionally determines z, then x also functionally determines the union of y and z. Next is pseudo transitive rule. It says that if x determines functionally determines the value of y and union of w and y functionally determines the set z, then union of w and x also functionally determines the set of attributes z. So these were the inference rules which we have discussed in the last lecture, in the previous lecture on normalization. Next topic was the closure of f, where f is the set of all function dependencies that are specified on a relation schema R. Closure of f is denoted as f superscripted by the symbol plus. So it is the set of closure of f is the set of all dependencies that include f as well as all the dependencies that can be inferred or deduced from f. That means the dependencies that are specified on the relation schema as well as those dependencies which we can infer from the given dependencies. So the set of all the dependencies is called the closure of f. Then we have discussed about the general concept of normalization. It is a logical design method which minimizes data redundancy and reduces design flaws. So all the formal and informal guidelines we have discussed previously, they are used in this process of normalization. Normalization process provides database designers with a formal framework for analyzing relation schemas based on their keys and on the functional dependencies among their attributes. A series of normal form tests that can be carried out on individual relation schemas so that the relational database can be normalized to any desired degree. So in this process, in normalization, we actually perform a series of tests that on the individual relation schemas so that the relational database can be normalized to any desired degree. Different levels of normal form tests are performed. The relation schemas which does not satisfy those requirements, then they do not meet certain normal form tests. They are decomposed into smaller relation schemas. So the relation schemas that do not meet or that do not pass those normal form tests, they are decomposed further into smaller relation schemas that meet the tests and hence possess the desirable properties. So here we can see that first of all we take relations and then we analyze them individually and collectively, and then we decompose them in order to meet the desirable properties. So normalization is actually a top-down design methodology which involves evaluating each relation against the criteria for normal forms and decomposing the relations as necessary. That is why normalization process could also be considered as relational design by analysis. So now we can formally define the process of normalization as a process of analyzing the given relation schemas based on their functional dependencies and primary keys to achieve the desirable properties. And what are these desirable properties? First is minimizing redundancy. Second property that is desirable is minimizing insertion, deletion, and update anomalies. Third property that we want to satisfy is lossless join property. It states that no spurious tuples are generated when relations are united or reunited through a natural join operation. That means when we decompose the relations and after decomposition If we reunite the decomposed relations, uh, then the result of that natural join operation on the decomposed relation should not generate any spurious or wrong information in the relation. That should be similar as the data or the information in the resultant relation should be similar as in the original relation before decomposition. Then is dependency preservation property. It ensures that each functional dependency is represented in some individual relation resulting after decomposition. That means if a relation there are functional dependencies in the relation before decomposition, then those functional dependencies should not lose. They must exist in any one of the decomposed relations as it is. So there are various normal forms to which we can normalize our relations. First normal form, second normal form, third normal form, Boyce-Codd normal form. Out of these, second, third and Boyce-Codd normal form, they are based on functional dependencies and keys. Fourth normal form is based on multi-valued dependencies and keys. Fifth normal form is based on joint dependencies and keys. So in these normal forms, up to the designer's goal is to normalize the database up to Boyce-Codd normal form, third normal form, or maximum of fourth normal form. Beyond that are the higher normal forms, which are rarely used or rarely required for normalizing the database. Before discussing these normal forms, we must have the knowledge of the terminology we will be using in those normal forms, the various definitions of keys and attributes participating in keys. First is super key. So what is super key of a relation schema R? It is a set of attributes of R with the property that no two tuples in any legal relation state of R will have equal value or same value for those attributes. That means for the set S, no two tuples T1 and T2 will have T1S equals to T2S. That means the value of those attributes will be different for all the tuples in the relation. It will be unique for a tuple. And key is a minimal super key, or the meaning of minimal super key is that it is a super key with the additional property that removal of any attribute from the super key will cause that key not to be a super key anymore. That means if we have a super key k, and if we remove some attribute from that super key, then the remaining set of attribute will not be a super key anymore. So a super key with such a property is called the key of the relation. Candidate key. If a relation schema has more than one key, then each of that key is called a candidate key. Primary key is one of the candidate keys is arbitrarily designated to be the primary key, and the others are called secondary keys. Next is prime attribute. A prime attribute must be a member of some candidate key. So in any attribute that belongs to some candidate key or some key of the relation, that is called prime attribute. And a non-prime attribute is not a prime attribute. That means it does not belong to any candidate key of the relation, or it's not a member of any candidate key. These two terms will be used in the while we will be defining the normal forms. So let's learn about the first normal form. It disallows multi-valued attributes, composite attributes, their combinations, repeating columns or attributes within a row or a tuple, relations within relations, or relations as attribute values within tuples. So the only attribute values permitted by first normal form are single atomic or indivisible values. It is considered to be the part of the definition of relation. That means first normal form is defined as a part of the while we are defining the relation. So formal definition is a relation is in first normal form if the domain of each attribute contains only atomic values, and the value of each attribute contains only a single value from that domain. That means the attributes are neither composite nor multi-valued. So first normal forming actually simplifies attributes and hence the queries become easier. Remedy for the relations which does not follow first normal form, the remedy for such relations is form new relations for each non-atomic attribute or nested relation. Now the first normal form will be more clear by the examples which are given here. First of all, consider a relation customer in which database designer wants to store the information of a customer and his telephone number. This relation is not in first normal form. How? Here we can see that the attribute telephone number contains multiple values. For the second record corresponding to the customer ID 456, the telephone number attribute contains two values. There are two telephone numbers for the customer. Therefore, due to this attribute, multi-valued attribute, this relation is violating the first normal form. In order to normalize this relation into first normal form, we have to decompose that relation into two relations. Here the information like customer ID, customer's name, first name and surname, that is put into separate relation, and the customer ID and telephone number is put into the other relation. Here customer ID is primary key for the first table and telephone number is the primary key for the second table. So this design compiles with first normal form. Another example is consider a relation employee which stores the information about employee and the department and the skills that employee possess. So here are the fields: employee number, employee's name, department number, department name, and the skills that the employee possess. So here we can see that the table is not in first normal form because the attribute skills contain multiple values. Next, the how we can normalize that relation into first normal form. For each value in the skills attribute, we create a tuple, that is each value of skill is now corresponding to an individual tuple. But here we can see that there is a redundancy of data, like in the first three records, employee number, employee name, department number and department name, they are repeated. In the second record the data is repeated two times. In the third corresponding to the employee number, third it is repeated three times. So there is a lot of redundancy of data when we produce or when we generate a separate tuple, create a separate tuple for each value of the multi-valued attribute in the relation. So for minimizing this redundancy, we have to decompose this relation into further smaller relations, and these are: first is imp, which will contain the employee number as the primary key, name of the employee and department number, and second is department, which will contain department number and department name. So here the relationship between imp and department is through foreign key, that is department number. Then employee and skills, the relation between employee skills is shown through the relationship between employees and skills is shown through the table imp skills, which contains the skills and imp number, two attributes, as the primary key. So these three relations are in first normal form and contains as much possible as less redundancy. Now we can see that here is a redundancy of employee number in the imp skills, but the extent of redundancy is much less as in case of the original table. Consider the table 1, which contains the information about the books. First is title of the book, then second and third field are authors of the book, fourth is the ISBN, then subject, pages and publisher. Here we can see that this relation or this table is violating the two conditions of first normal form. One is the repeating columns, that is author 1 and author 2 are repeated two times. Then second condition is multi-valued attribute. Here subject attribute is the multi-valued attribute because it contains two values for the same book. One is MySQL and other is computers. So after normalization, the table 1 is in the form like this. Now again here we can see that for each subject, each value of the subject attribute, we have created a new tuple, but again this relation results in redundancy, but it contains redundant data for the attributes. Therefore a better solution to our problem would be to separate the data into different tables. First is book table, that will contain only the information about the books. Author table, that will include the information about the author. Subject table, that will store the information regarding the subject only. So here are the tables. You can see that in the book table, the ISBN is the primary key. In the author table, author ID is the primary key. In the subject table, subject ID is the primary key. There are no multi-valued or composite attributes, and hence these three tables are in first normal form. Now we can define relationships between these tables through further two more tables, that is book author table, that represents relationship between books and authors, and book subject table, that represents relationship between books and subject. So finally we got five relations which are in first normal form: book table, subject table, author table, book author table, and book subject table. Second normal form, it uses the concepts of full functional dependency and primary key. Now what is full functional dependency? A functional dependency x or y is a full functional dependency if removal of any attribute a from x means the functional dependency does not hold anymore. That is, for any attribute a belonging to x, x minus a does not functionally determine y. On the other hand, opposite to full functional dependency is the partial functional dependency, which states that if functional dependency x tends to y is a partial functional dependency if some attribute a belonging to x exists and it can be removed from the set of attributes x from the determinant set, but still the dependency holds. So full functional dependency is such a functional dependency where if we remove some attributes from the determinant set, then the remaining set still determines the dependent set. This is called partial functional dependency, but in case of full functional dependency we cannot remove any attributes from the determinant set, otherwise the functional dependency will not hold anymore. The concept of full function dependency will be more clear from this example. Consider this relation in project that contains information about the employee and the projects on which that employee works. Here three functional dependencies are specified on the relation. First functional dependency, employee ID and P number collectively determines the value of hours. This is a full function dependency because neither employee ID alone determines the value of hours nor the project number alone determines the value of hours. Therefore the dependent set is fully functionally dependent on the determinant set. We cannot remove any attribute from the left hand side or the determinant set. But the functional dependency, employee ID and project number determines ename, is not a full function dependency because if we remove project number from the determinant set, still the function dependency employee ID determines employee name holds. Therefore this dependency is a partial functional dependency. Similarly, if we remove employee ID from the determinant set, then the project number alone is still determining the value of project name and project location. Therefore the function dependency imp ID and P number determining project name and project location is not a full functional dependency, or you can say it is a partial dependency, partial function dependency. So now we can formally define the second normal form. Its relation schema R is in second normal form if every non-prime attribute A in R is fully functionally dependent on the primary key of R, or a relation schema R is in second normal form if every non-prime attribute A in R is not partially dependent on any key of R. So definition of second normal form states that a relation schema will be in second normal form if it is in first normal form, first of all, and if every non-prime attribute, that is the attribute which doesn't belong to any candidate key or any key of the relation, is fully functionally dependent on the primary key of relation. So this normal form improves the data integrity by preventing various